Alright, so last video we talked about lines in space. In this video we're going to be talking about planes in space. So remember, a line is defined by a point and a vector. A plane is also defined by a point and with the normal vector n. And remember, the vector n is orthogonal or perpendicular to the plane. So if you have the point, you know where the plane runs through, and if you have the normal vector n, you know which way the plane tilts or what direction it faces. Alright, so how do we come up with an equation of a plane? Let's take a look at the image in the middle where we have a plane represented by the four blue lines. So let's say we have a point on the plane, P0, and its coordinates are x0, y0, and z0. And we'll put another point on the plane. We can call that point P, and its coordinates will just be x, y, and z. We can create a vector starting from P0 going to P. Now this vector is going to be along that plane. And then remember, to define a plane, we need to have a normal vector n. And this is going to come out of the plane perpendicularly. Since vector P not P is on the plane, that means that the normal vector n is going to be perpendicular to that. And recall that if two vectors are perpendicular to each other, their dot product would equal 0. This means we can indicate that vector P not P and vector n are perpendicular by writing n dot P not P equals 0. So remember, in 3D, a vector has an x component, a y component, and a z component. Vector P not P can be found by taking the final minus the initial. So P is x, y, z, and P naught is x naught, y naught, z naught. So the x component is x minus x naught, the y component is y minus y naught, and the z component is z minus z naught. For normal vector n, we'll just say that its components are a, b, and c. So substituting these values in, we'll have a vector of components a, b, and c dotted with the vector with components x minus x naught, y minus y naught, and z minus z naught. And this equals 0. Performing the dot product, we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught. This equals 0. So this is the equation of a plane. X naught, y naught, and z naught is a point on the plane. If we wanted to take this further, we could. We can go ahead and distribute the a, the b, and the c. We'll move a x naught, b y naught, and c z naught to the other side of the equation. And then x naught, y naught, and z naught are all constants in addition to a, b, and c. So we can just say the sum of those is just the constant d. And the equation of a plane can also be represented by this, in which x, y, and z are all variables. So now let's go over plotting a plane and finding the normal vector n. So negative 6x plus 2y plus 3z equals 6 is an equation of a plane. Now before I go through the process of how to plot it and finding the normal vector, I'm going to show you an example in 2 dimensions first, so you can understand the idea of why I do what I do. So in 2D, we have an equation of a line. Let's say 2x plus 4y equals 6. Now this equation is in standard form because we have a coefficient times x plus a coefficient times y equals a constant. Usually we'd like to put this in slope-intercept form so we can plot the line easier. The equation in standard form is y equals negative half x plus 3 halves. Now from here, you may remember that it's very easy to plot the line because we have the y-intercept 0, 3 halves, and we can put a point there, and we have the slope, so we can go 2 across, 1 down, and get our line like that. But I'm going to show you another method that is along the lines of how we would plot our plane in 3D. So what we can do to find the line is to get 2 points, and we can do that by getting the x-intercept and the y-intercept. So let's take our standard form equation again. So we can first find the y-intercept by plugging in 0 for x. So if 0 is an x, 0 times 2 would be a 0, and we're left with 4y equals 6, which means y would equal 6 over 4, or 3 halves. Now we do the same thing for the other variable, so let's plug in 0 for y. When we do so, this whole term turns into 0, and we're left with 2x equals 6, in which x equals 3. So we have our points 0, 3 halves, and 3, 0. So we can plot this on the graph. So first we'll plot 0, 3 halves, that'd be right there, and then we'll plot 3, 0, right there. And we can run a line through these 2 points. And that's how we can plot a line given the standard form equation. So let's say there's another line that's perpendicular to this line. The slope of the green line is negative 1/2 because that's the number in front of the x. If you remember, we can get the slope of the line that's perpendicular to the green line by taking the negative reciprocal of negative 1/2. So the negative reciprocal of negative 1/2 is positive 2 over 1, or just positive 2. Now let me show you something interesting, and this is how we get our normal vector. So I'll go ahead and remove this for now. If we take a look at the coefficients of our equation in standard form, we have a 2 in front of the x and a 4 in front of the y. That is actually just our normal vector. If we start at the origin 0, 0, and go 2 to the right and 4 up, you'll notice that this vector is also perpendicular to the green line. Now let's go back to our plane equation, negative 6x plus 2y plus 3z equals 6. To plot the plane, we want to get 3 points from the 3 intercepts for each variable. So first we can zero out the y term and the z term. And this would leave us with negative 6 equals 6, which means x equals negative 1 when y and z are 0. So we can write that for our first point. Now let's zero out x and z. We are left with 2y equals 6, in which y equals 3 when x and z are equal to 0. So our second point is 0, 3, 0. And finally, we can plug in 0 for x and y. This term is 0 and this term is 0, so we're left with 3z equals to 6, and leaves us with z equals 2 when x and y are 0. So our third point is 0, 0, 2. So we can start plotting this. So first here's negative 1, 0, 0, and then 0, 3, 0, and then 0, 0, 2. So with these 3 points, we can make out a triangle. And this triangle is a piece of the infinite plane. So its normal vector that goes through it is the normal vector of the plane. And remember, to get the normal vector, we look at the coefficients in the standard form equation. Negative 6, 2, and 3. And that's basically it. So now let's do some examples. Number 1, find an equation of the plane through the point 2, 5, 4 perpendicular to the vector -1, 3, 5. Alright, let's start by writing out the component equation of the plane. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So to get a plane, we need a point on the plane and the plane's a normal vector. So here we're given a point on the plane. Remember, we wrote it as x naught, y naught, z naught. And they're telling us that the plane goes to the point 2, 5, 4. And then the normal vector, we said had components of a, b, and c. Normal and perpendicular mean the same thing, and they're saying that the perpendicular vector is -1, 3, and 5. So the normal vector is -1, 3, and 5. So we can plug in our values. A is -1 times x minus x naught, which is 2, plus b is 3, we have y minus 5, plus c is 5, times z minus z naught, which is 4, equals 0. And then since -1 is a coefficient, we don't need to include the 1. So our equation of this plane is this. Alright, for example 2, find an equation of a plane through the points -3, 0, 1, 4, 7, 2, and 2, -1, 5. So if we were to find the plane from 3 points, then those 3 points would need to be non-collinear, which means they're all 3 not on the same line, which we do have in this case. So given 3 non-collinear points, they would form a triangle. So let's just label these 3 points A, B, and C. And then I'll just roughly place them in the formation of a triangle. Alright, I'm going to put up the equation of the plane again. So A times x minus x naught plus b times y minus y naught plus c z times z minus z naught equals 0. So remember, we are looking for a point on the plane and the normal vector to the plane. So we're given 3 points that are on the plane. We can choose any one of them to be our x naught, y naught, z naught. I'm just going to choose point A. And then we are looking for a vector perpendicular to this plane. So from these 3 points, we are able to make a triangle, which is part of the plane. And if we can find the normal vector to this, then we have the normal vector to the plane as well. Recall the cross product takes 2 vectors and finds another vector perpendicular to both those vectors. We can make out 2 vectors from this triangle that shares the same point as their tail. So let's choose point A. We could use the side going from A to C and the side going from A to B. If we take the cross product of AB and AC, we'll get our normal vector. So remember, to get vectors, we're taking their final point and we're subtracting their components from the components of the initial point. So we're doing B minus A. So we'll have for vector AB 4 minus a -3, which is a 7 minus 0, which is a 7, and a 2 minus a 1, which is a 1. And then for vector AC, we're doing a 2 minus a -3, which is a 5, a -1 minus a 0, which is a -1, and a 5 minus a 1, which is a 4. So again, for the cross product, we're doing a 3×3 determinant. And then we get for the x component, 7 times 4, which is 28, minus 1 times -1, which is a -1. And then for the y component, we're adding a negative. And then we do 7 times 4 minus 1 times 5. And then for the z component, 7 times a negative 1, which is negative 7, minus 7 times 5, 35. So AB cross AC equals 29, negative 23, and negative 42. This is going to be the normal vector n orthogonal to the plane. So plugging in a, b, c, x naught, y naught, and z naught into the plane equation, we will have 29 times x, okay, minus negative or plus 3, minus 23, and y minus 0, or just put a y, minus 42, z minus 1 equals 0. And this is the equation of a plane given those 3 points. Alright, number 3, find the equation of a plane through the point 1, negative 2, 3, parallel to the plane 3x minus 6y plus 5z equals 2. So let me write out the plane equation again. Again, we are looking for a point on the plane, x naught, y naught, z naught. We're also looking for the normal vector of the plane. So we're already given a point on the plane, 1, negative 2, 3. And we're trying to find the normal vector. The plane we're trying to find is parallel to another plane. So let me draw a visual. So let's say that these 2 green planes are parallel. If 2 planes are parallel, they share the same normal vector. Since the plane we're trying to find is parallel to the plane 3x minus 6y plus 5z equals 2, we will find the normal vector of the plane that we're given because they both share the same normal vector. So if we take the coefficients, we'll get that n equals 3, negative 6, and 5. So our equation of the plane is 3 times x minus 1 minus 6 y plus 2 plus 5 times z minus 3 equals 0. Now let's talk about the distance from a point to a plane. So let me draw a picture. So we have point Q, which is not on the plane, and we want to find the distance from it to the plane. And when we are talking about the distance, we want the shortest distance. If we were to draw a line representing the shortest distance from point Q to the plane, this line would be orthogonal to the plane. And we could represent this distance with the variable d. The vector that is orthogonal to the plane is vector n, the normal vector. And let's say we were given a point on the plane, point P. If we draw a vector starting from point P going to point Q, you notice that vector PQ isn't necessarily the shortest distance because that vector isn't orthogonal to the plane. However, there is a point on the plane where if you start from there and you go in the direction of the normal vector, you'll end up at Q in the shortest distance. But we just don't know what that point is. Being at a diagonal, vector PQ can be broken into different components. So we can have one going horizontally, we can have one going forwards and back, but we're not interested in those. We're just interested in the component that goes along the distance, d. And this direction is in the direction of the normal vector n. So what we can do is we can take the projection of PQ onto n to get that vector. So we can write D equals the projection of PQ onto N. However, we just want the distance, or the magnitude, so we can put bars around this. Now recall the projection formula. If we have a projection of vector A onto vector B, this equals A dot B over the magnitude of B squared times B. And if we take the magnitude of this, we will get the magnitude of A dot B divided by the magnitude of B. So we'll go back to the distance equation and we'll write that in that form. So this means that the distance equals the magnitude of PQ dot N divided by the magnitude of N. And this is the equation of the distance between a point and a plane. Alright, let's do example 4. Find the distance from the point 4, 5, negative 1 to the plane 3x minus 4y plus 9z equals 12. First, I'm going to write down the equation for the distance from a point to the plane for reference. So let's take a look at what we have. First, they give us the point that is off the plane. This is going to be our second point in the vector, so we can just call this point Q. Next, they give us the equation of the plane, and from this, we can get the normal vector by taking the coefficients. So this would be 3, negative 4, and 9. So now we need to find a point on the plane. We can use the equation of the plane to find one of its intercepts. Let's say we want to find the x-intercept. We get the x-intercept by plugging in a 0 for y and a 0 for z. So if we do that, our equation is 3x equals 12. Which means x equals 4 when y equals 0 and z equals 0. So a point on the plane is 4, 0, 0. We can call this point P, which is the start of the vector. And we can get vector PQ by subtracting the components of vector Q by the components of vector P. So 4 minus 4 is 0. 5 minus 0 is a 5. Negative 1 minus a 0 is a negative 1. So now we can plug in some values. Vector PQ, 0, 5, negative 1. We're dotting that with vector N, 3, negative 4, 9. And we're dividing this by the magnitude of vector N. So the distance between the point and the plane is approximately equal to 10.3 units. Now let's talk about the angle between planes. So let's recall the formula for the angle between two vectors. If A and B are both vectors and theta is the angle between them, then the equation is theta equals the inverse cosine of A dot B divided by the magnitude of A times the magnitude of B. If we draw normal vectors for each plane, we can call n1 the normal vector for the green plane and n2 for the normal vector for the blue plane. The angle between these two normal vectors is equivalent to the angle between the planes. So we can find the angle between both planes with the following formula. Theta equals the inverse cosine of n1 dot n2 over the magnitude of n1 times the magnitude of n2. So let's do this related example. Number 5, find the angle between the planes 4x plus 4y plus 6z equals 7 and x minus 2y plus z equals 5. Alright, so we would need normal vectors for both of the planes. if this is the first plane, we can write its normal vector as n1 equals, and then if we take the coefficients, it's 4, 4, 6. And then if this is the second plane, n2, the normal vector for this plane is equal to 1, negative 2, 1. So if we put these into the equation, we can get the inverse cosine of n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. So the angle between these two planes equals 84.32 degrees or 1.47 radians.